Hello, folks. So, as you're watching this, I'm probably in New Orleans, learning about science stuff. So, this video is meant to try to keep you up to date with material. Now, there may be some overlap as I'm making this well in advance. Not well, but at least over a week in advance of where we will. So if there's a little bit of overlap, I apologize, but with that in mind, we'll sort that out later. We'll go ahead and get started. These next two videos will catch you up, and so we won't really be behind. This will be starting in the middle of Chapter 8. Well, we'll start with talking about driving forces. The idea is that a driving force is the essentially the energy that is going to push the reaction forward. Every reaction is going to try to achieve a more stable state. The goal is, it's like a rock rolling down a hill. When it reaches the bottom, it's going to eventually run out of energy and stop moving. All reactions are like that, where we have a high point and a low point, and we're always going to try to get from a high point to a low point. Now, these driving forces could be in the form of an energy change. It's going to release energy as it relaxes to a more stable state, but it also could be a change in entropy, which is randomness. Things will naturally want to mix together. You try to put salt into water, and slowly but surely the salt will dissolve. Yes, it will dissolve faster if you stir, but it will naturally want to mix into the water because of the solubility issues. So things like that. Gases. If I mix in some gas, like oxygen, into a room filled with nitrogen, given enough time, the oxygen will fully integrate itself into the room. Now, there's ways to speed up that mixing, but naturally that will want to occur, even if there's no change in heat. Now, since this chapter is largely about aqueous reactions, these driving forces can come in three different forms, one of which is a precipitation reaction, which is the formation of a solid. When it forms a solid, it kind of causes a thing to crash out of solution, and this rapid crystallization drives the reaction forward. You've seen this when we added the silver nitrate to the chloride containing test tube in our first lab, that it formed that white solid. Now there's acid-base neutralization reactions. Acids are things that donate a H+. Bases are things that have an OH-. Naturally, H+ and OH- will want to combine together to form water. The formation of water is a very low energy state, and this neutralization, this canceling of plus and minus, is going to drive all acid-base reactions to completion. The one that's a little bit harder to understand is an oxidation-reduction reaction. In an oxidation-reduction reaction, we are going to transfer electrons from one element to the other to form a lower energy products. Like if I mix, gold 3+ with, say, zinc solid, I'm going to get zinc 2+ and gold solid. The exact amounts of each one will depend on the electrons transferred, but the electrons are going to be lost by zinc and gained by gold. Things like that. That if I mix HCl into certain metals, the metals are going to dissolve, and so the metals lose electrons, and HCl is going to form hydrogen gas. These are such things where we're going to donate electrons and accept electrons to get a lower energy state. These are three big driving forces that we'll be able to look at, and we're going to take each one in turn. Now, before that, we need to understand how solutes dissolve. When we understand that, when a solid dissolves in water, it is said to be soluble. If it remains undissolved, it's said to be insoluble. Now, the dissolution occurs when via solvation, when a compound or series of ions dissociate and are hydrated by the water. In order to do this, you need to understand dipole moments. The idea that dissolution works because of the attraction of opposite charges, or the similar interactions, the intermolecular attractive forces. Now, water, because of its difference in electronegativity and its it has some symmetry, but there's a regions of non-symmetry there, that it's going to contain a partial positives around the hydrogen and a partial negative around the oxygen, the delta pluses and delta minuses. So we're going to use the Greek letter delta. We've seen that before. That's our dipole. So the oxygen has a negative dipole and the hydrogens have positive dipoles. Well, all these water molecules with their positive and negative dipoles are interacting with other water molecules. But when we dissolve something in there, water being the greatest quantity object, the solvent, the cations will get surrounded by the negative portion of water. And so there's all the pluses of the cations are going to see a bunch of different oxygens with their negatives around them. And the anions are going to see a bunch of the hydrogens around them. So we're going to surround them with water molecules angled so that the H pluses and the partial positives are going to see the negative charges, and the partial negatives are going to see the positive charges. And there's going to be a bunch of water in between. These chlorides and sodiums can still interact with each other vaguely, but because there's a lot of water that's going to be in between them, they're going to be somewhat shielded. And so even if they do bump into each other, for the most part, these guys will be like two trains passing in the night. So even though the anions are can be close by each other, they're largely shielded by by a large amount of water molecules, so they don't really get very much interaction with each other. Now, occasionally, as we'll see, the interactions between ion and ion are much stronger attraction between the cation and anion than it is with the water. In this case, these guys will bind together into our ionic structures and precipitate rapidly from solution, or simply not really dissolve much at all. But for the most part, the large amount of water molecules can separate and dissolve most ionic solids. Non-ionic compounds can still dissolve if they contain partial charges. Things like ethanol or sugar have a series of OH bonds, and these create the same partial positive, partial negatives in these covalent bonds as you would see in water. And so they can still dissolve. It's just they dissolve as a big lump molecule. But generally speaking, if they don't have any partial charges, they won't dissolve in water. As you'll potentially see next semester, organic compounds will dissolve organic compounds. Aqueous compounds will dissolve aqueous compounds. So if they don't have partial charges, They're probably organic and they'll dissolve in other organic situations. Now, we can break compounds into three soluble compounds into three different classes. They're not all going to have the same properties. That there's some compounds, when they fully dissociate into water, will strongly conduct electricity. These are referred to as strong electrolytes. Basically, when they hit the water, they form a lot of ions. And a lot of ions means it's going to conduct a lot of electricity. And with that in mind, you're gonna see a strong current if you try to flow electricity through them. When a compound dissolves but does not directly dissociate into water, it will not conduct any electricity. Sugar is an example of that. It dissolves, but it does not break apart. These guys are non-electrolytes. These guys are often considered molecular compounds. Soluble organic. Ethanol is an example, as is sugar, as is a lot of different things like that. Occasionally, you'll get the in-between. Compound will dissolve and will start to dissociate, but it's only a partial dissociation into water. Because it only partially dissociates, it only makes a few ions. These guys will conduct electricity weakly. These guys are called weak electrolytes for that reason. Now, we want to look at strong electrolytes are composed of soluble ionic compounds and strong acids and strong bases. Sodium chloride is a soluble ionic compound. KOH is a strong base. Sulfuric acid is a strong acid. There's only so many strong acids and strong bases out there. It's pretty easy to, once you know them, if you connect them, they will conduct electricity very strongly. Non-electrolytes are chiefly soluble molecular compounds. The first compound, CH3OH, is methanol. C6H12O6 is glucose. Too far. These guys, lots of carbons, lots of hydrogens, lots of oxygens, but there are no ions, no metals in there. Weak electrolytes have properties of both ionic and molecular compounds. Weak acids and weak bases are weak electrolytes. They ionize to a small degree, but largely remain intact. So, acetic acid, which is HC2H3O2, carbonic acid, and ammonia are examples of weak acids and weak bases. That would be weak electrolytes. Now, one of our classes of compounds is precipitation reactions. So the driving force is you mix two aqueous solutions. You mix two basically liquids. They're not pure liquids. They're saltwater solutions, essentially, that look clear or colored, but there's no solid present. And the second you mix them together, boom, solid. You form a solid that precipitates out. And that's how you know it goes to products. So a precipitate is an insoluble solid that forms out of solution. And so long as one out of the two products is insoluble, the precipitation reaction will occur. It is a driving force. Now, while there are rules, and you can use those rules to determine whether precipitation should occur, there's also tables, and I'll show you the tables later. But the first two rules are most important because these are the always rules. But when considering whether precipitation will occur, You need to first write down the products of a double replacement reaction. So you simply, looking up here, we have sodium and iron. A double replacement means the sodium takes the place of the iron, and iron takes the place of the sodium. Sodium is +1, iron is 2 plus. So +1 matches with -1, so we have 2 sodium chlorides. The +2 matches with -1, so we need 2 hydroxides. And then we look at, so we have iron hydroxide and sodium chloride. Step 2, we use our rules or table to determine the solubility. And this is the very important thing. If any product is insoluble, a precipitation occurs. If all of the products are soluble, we say no reaction occurs. If that's aqueous and that's aqueous, no reaction will occur. Now, I'll read the rules, but we'll look at the table in a minute. Rule 1, all group 1 elements, so that means lithium, sodium, potassium, rubidium, cesium, and francium, all +1 cations, and ammonium are soluble. So whenever you see an element with a compound with these guys or ammonium, it will always dissolve. Yes, you can get these guys as a solid by drying out the water. But if you mix any water, these guys should dissolve. So sodium hydroxide should dissolve in the presence of water. Rule 2, nitrates, chlorates, perchlorates, and acetates are always soluble, which is why we can use silver nitrate. Silver nitrate, soluble. We saw perchlorate, silver perchlorate was, or silver chlorate was soluble. Any sort of acetates are always soluble. From there, these are sometimes rules. For example, chloride, bromide, and iodide, group 7B elements, are soluble except when in the presence of silver, lead, or mercury. So silver chloride precipitates, silver bromide precipitates, silver iodide precipitates, lead iodide, lead chloride, lead bromide precipitates, mercury 1 precipitates. Now, another exception. So rule 4, except with compounds in group 1 and ammonium, carbonates, sulfites, phosphates, and chromates are insoluble, meaning any sort of carbonate except for with these group metals and ammonium are insoluble. So sodium carbonate, which is washing soda, dissolves. But iron carbonate does not. Zinc carbonate does not. Any transition metal carbonate, or say barium carbonate or magnesium carbonate, will not. With the exception of group 1 and barium. Hydroxides and sulfides are insoluble. So sodium hydroxide, lithium hydroxide, or barium hydroxide will dissolve, but any other hydroxides will not. So this is our rule. Rule 5 tells us that iron hydroxide is insoluble. Iron hydroxide forms a solid. Because with the exception of guideline 1, rule 1, and barium, all hydroxides are insoluble. And with the exception of guideline 2, all silver, mercury, and lead are insoluble. So silver nitrate, silver chlorate, silver perchlorate, and silver acetate are soluble, but no other silver compounds will be soluble. No other silver compounds will dissolve. No other mercury or lead will dissolve. And with the exception of compounds calcium, strontium, and barium, the ions listed in guideline 6 and the ions listed in guidance 6. Sulfates are soluble. So sulfate's soluble with everything except for silver, mercury, and lead, and calcium sulfate, strontium sulfate, and barium sulfate. So magnesium sulfate dissolves. Beryllium sulfate dissolves. Iron sulfate dissolves, but not these few exceptions. As I said, these are rules that I don't really need you to learn. Rule 1 and Rule 2 might be worth writing down, but I don't need you to learn that because on a test, you would be given a chart just like this. So how do you read the chart? So if you look down there, it says soluble, S. SS is slightly soluble, means it will dissolve a little bit, but not very much. I is insoluble, less than 0.1 gram dissolves, and D decomposes, so it wouldn't even form a compound, it would just break down and do weird stuff. So reading that, you'd look at, here's our ions, would cross-reference them and look for S, SS, or I. So group 1, all these guys are soluble. Rule 2, all these guys are soluble. Magnesium is soluble with group 1, rule 1, with chlorides, with sulfate, but not these guys. And magnesium sulfide would decompose, and not with this guy. Calcium and strontium, you cross-reference these guys. Okay, insoluble, insoluble. Calcium is slightly soluble. Barium, soluble, soluble, insoluble, insoluble, and soluble with these guys. Nickel, iron 2, zinc 2, copper 2. Soluble with these cases, but not with those. Silver. So it turns out silver is slightly soluble with sulfate, but we'll just say it's insoluble because it's only in the one rule said the only way it's soluble is with rule 1. And then mercury and lead. So anything that's not on the chart, you'll have to take your best guess at. Most transition metals are going to be soluble, except for these guys and hydroxide and sulfide. But so that's how you read that. You're cross-referencing and looking. If I have barium chloride, it's S, which doesn't stand for solid, stands for soluble, so it'd form aqueous. Calcium sulfate, I. That means it's going to form a solid if you mix those together, any amount of calcium and sulfate. So, with that in mind, so what are we going to do with these guys? Recall that aqueous compounds dissolved in water can be classified as electrolytes or non-electrolytes, depending on whether ionic or molecular. Well, ionic compounds, if they're electrolytes, can be separated into their cations and anions. Now, this is only true for aqueous solutions of strong electrolytes. This is not true for solids, it's not true for liquids, it's not true for gases. They do not break apart spontaneously in solid, liquid, or gas form. They only break apart when they're in aqueous. So let's look at that. Lead nitrate, which is PbNO3 2, breaks apart into lead 2 plus and nitrate 2 nitrate 1 minuses. Please note that the nitrate is the full anion. It's not the nitrate does not break into nitrogens and oxygens. The nitrate stays one big clump of anion. You draw the Lewis structure for the nitrate, not for 2 nitrogens and 6 oxygens. You draw it for 1 NO3, 1 minus. So, because this is aqueous, it would break apart. This will lead us to 2 different ways of writing the same chemical equation. One is the total equation, which is our standard method, where all compounds are left uncharged, and the ionic equation, where all strong electrolytes that are aqueous are allowed to split into their individual charged ions. So total is how we've been writing it. Ionic is the new way, where we break down everything that's aqueous into its charges, its cation and anion pairs. Remember, do not overly break things apart. I every year or so I see someone who breaks apart things weird. If this was PbCl, let's say it's MgCl2. The Cl2 is two chlorides. It's not Cl2 chlorine gas. So we got to remember how things are going to break down. Don't forget that. So there's a lot of words on this slide, but let's take it and look at it piece by piece. So lead, nitrate, and potassium chromate, both of those aqueous, forms lead chromate solid and potassium nitrate aqueous. That is the total ionic equation. It's balanced, so there's two chromiums. One chromium on both sides, two potassiums on both sides, two nitrates on both sides, and one lead on both sides. Now, if everything aqueous is allowed to split, it forms a lead 2 plus, and that 2 goes into from a subscript to a coefficient, 2 nitrates. That subscript there, it's not K2, it's now 2K plus. And chromate, 2 minus. The lead chromate is a solid and stays together. All solids are left as they are. And 2 potassiums and 2 nitrates are left, splitting apart. So as you look at that, the 2 nitrates on the left and the 2 nitrates on the right are the same and they remain unchanged. The 2 potassiums on the left and on the right are the same, they are unchanged. The only thing that really changes is the lead 2 plus goes to lead chromate solid, and the chromate 2 minus aqueous goes to lead chromate solid. So the nitrate and potassium are said to be spectator ions. Ions that they don't change state, they don't change charge. They essentially spectate on the action. They're floating around, dissolved in water, but they aren't actually doing anything. They're like those trains passing in the night. They don't interact with anything. They're just there floating around. It's like the idea of a ghost watching you. The ghost might be seeing what's going on, but if that ghost cannot interact with reality, you won't know it's there. The spectator ions, we don't know they're there. So they don't actually do anything. If we were to remove all spectator ions, we get what's called the net ionic equation. So it's the net change we're looking at. We're looking at what has changed between one reaction and the other, and we get the net ionic equation. This net ionic equation just shows only the ions and the compounds that directly participate in a reaction. Some equations may not have any spectator ions, but one of the key things is if every reactant and every product are made up of spectator ions, then there is no driving force. If there is no driving force, no reaction occurs. I know we want to think they swapped places in a double displacement, but if there's not a driving force to actually swap, to keep the swaps together, they swap back. It's like you go to a dance and you go to the hoedown and you swap swing your partner around and around, and then you swap partners, and you dance with them for a bit, and then you swap back. Just because you swap partners doesn't mean a real connection was made. It's not until like you go, oh, you're a good dancer. Let's dance some more over here away from them. Then we make a real connection. Then the reaction takes place. This may be a reaction of love, but in this case, this is a reaction of precipitation. So in the case of this one, silver nitrate, aqueous, sodium chloride, aqueous, and silver chloride solid and sodium nitrate, aqueous. So silver and nitrate both being aqueous split apart, Ag plus NO3 minus. Sodium chloride, both aqueous, split apart into sodium plus and chloride minus. Well, silver chloride is a solid, so it stays together. But sodium nitrate is aqueous, and so we allow that to break apart. If we look, sodium plus cancels with sodium plus. NO3 minus cancels with NO3 minus. So the net ionic equation is silver plus and chloride minus goes to silver chloride solid. Looking at this one, potassium nitrate, calcium chloride react to form potassium chloride and calcium nitrate. If you flip them around and balance these guys out, it looks like we have a reaction. But if you break these guys apart into what they are, the ionic components, you look, everything is aqueous and stays aqueous. So 2 potassiums cancels with 2 potassiums. 2 nitrates cancels with 2 nitrates. 1 calcium cancels with 1 calcium, 2 plus, and 2 chlorides cancel with 2 chlorides. Because everything cancels, it is said to be no reaction. We may draw this as if a reaction were to occur, but really, no reaction is happening. So I'm going to take a break real quick and jump back and show some examples. I'm just going off book. These guys are not in the notes. That way we can stop here after I give some examples. Now, so we can have sodium sulfide plus calcium acetate does a net ionic. What first does a react? What are the products? Step 2. What are the states of matter? Step 3. What is the net ionic equation? And step 4. Does a reaction occur? So step 1. What are the products? We have Na plus, S2 minus, minus. So swapping these around, you're going to have calcium sulfide and 2 sodium acetates. Now, what are the solubilities? I'm going to go back to the PowerPoint and look at the chart. So sodium sulfide is soluble. Calcium acetate is soluble. Calcium sulfide is soluble. And sodium acetate is soluble. So in this particular one, aqueous, 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 aqueous. So split these guys apart. Let's look at this guy. 2 Na plus and S2 minus and Ca2 plus, and 2 acetate 2 minus, goes to Ca2 plus, and S2 minus, and 2Na plus, and 2C2H3O2 minus. That in mind, they cancel, they cancel, they cancel, and they cancel. Net ionic equation is nothing. So we'd say this is a no reaction. That's how it is. That's how it be. Because they all ended up aqueous. We may want to say they swapped, but no real swap has occurred. No real swap has occurred. Let's look at this one. Iron nitrate and let's see, sodium carbonate. I got it. So what are the products? Step 1. Nitrate is -1. Means iron is 2 plus. Carbonate is -2, and we see that -2. That's +1. We got a charge. So let's swap places. So we can have 2 NaNO3 +1 and -1. We do not want this. We do not want this. That is not what we want. So 2 NaNO3 and Fe2 plus mixes with CO3 2 minus to be neutral. 2 plus, 2 minus. Flip them down, 2 and 2 simplifies to 1 and 1. 1 iron, 1 iron. 1 carbonate, 1 carbonate. 2 sodiums, 2 sodiums, 2 nitrates, 2 nitrates. Let's go back to our PowerPoint. So, okay, we had iron nitrate. Iron, where's iron nitrate? Okay, that is soluble, so that's aqueous. Sodium carbonate, soluble, aqueous. Sodium nitrate, soluble, aqueous. And iron carbonate, insoluble, solid. So, with that in mind, I've labeled aqueous, 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 solid. So let's split apart all the things. So let's write the total ionic. We have iron 2 plus and 2 nitrates, 2 sodium pluses, and carbonate goes to 2 sodium pluses and 2 NO3 minuses and FeCO3 solid. So everything that is duplicated exactly cancels out. Our net ionic equation becomes iron 2 plus aqueous and carbonate 2 minus aqueous goes to iron carbonate solid. There we go. That is what we do. That's how we break it down. If any solid forms, that is our driving force. If there's no solid forming, no driving force. that is where we will stop this video. It might be a bit short, but that seems like a good place to stop.